Welcome to Digital Logic Design. Throughout this lecture, I'd like to request you to pause this video whenever you need it and keep pen and paper with you so that we can solve problems to consolidate our understanding. In this tutorial, we're going to give an introductory overview of digital logic circuits, logic gates such as NOT, AND, OR, and XOR gates, Boolean variables and expressions. The simplest binary element is a switch that has two states. If a given switch is controlled by an input variable x, such as shown here, then we'll say that the switch is open if x equals to 0 and closed if x equals to 1, as illustrated in the figure A. We'll use graphical symbol in figure B to represent switches in this lecture. Now let us consider a simple application of a switch, where the switch turns a small light bulb on or off. This action is accomplished with the circuit in the figure shown here. A battery provides the power source. The light bulb glows when a sufficient amount of current passes through it. The current flows when the switch is closed, that is when x is equals to 1. In this example, the input that causes changes in behavior of the circuit is the switch control x, right here. The output is defined as the state or condition of the light. So x is the input, state or condition of the light is the output. If the light is off, then we'll say L equals to 0. If the light is on, we'll say that L equals to 1. Using this convention, we can describe the state of the light as a function of the input variable x. Since L equals to 1 if x equals to 1, and L equals to 0 and x equals to 0, then we can simply write L of x equals to x. This simple logic expression describes the output, the light bulb, or output of the light, as a function of the input, the state of the switch. We say that L of x equals to x is a logic function and that x is an input variable. Consider now the possibility of using two switches to control the state of a light. Let x1 and x2 be the control inputs of these switches. These switches can be connected either in series or in parallel. Using a series connection, the light can be turned on only if both of these switches are closed. So if either switch is open, the light will be off. Now this behavior can be described using this function. So the light is on if both x1 and x2 are 1. And in all other combinations of these two variables, the light should be off. The dot symbol here is called the AND operator, and the circuit in the figure is set to implement a logical AND function. Now the parallel connection of two switches is given in this case. So in this case, the light will be on if either x1 or x2 switch is closed. The light will also be on if both switches are closed. So the light will be off only if both switches are open. The behavior can be described using this Boolean expression. So if L equals to 1, then x1 equal to 1 or x2 equal to 1, or both of them are 1. And the light is off only when both of them are 0. So this can be written as an expression, x1 plus x2. So the plus symbol here is the OR operator. So this is not basically x1 plus x2, this is x1 or x2. And the circuit in the figure is set to implement a logical OR function. Now it is important not to confuse the use of the plus symbol with its more common meaning, which is for arithmetic addition. Here it means OR. Now we can use more switches to build more complex circuits. In the series parallel configuration here, for example, we use 3 switches to control the light. The corresponding logic function is x1 or x2, because here x1 and x2 are in parallel, and x3 because both of them are the combination of x1 and x2 are in series with x3. So the main idea of all these is that a logic expression such as this one, x1 plus x2 times x3, can be implemented as a circuit, and conversely, a circuit has an equivalent logic expression, such as this one. So that's the key idea that you have to remember. So every Boolean logic expression has a corresponding logic circuit, and vice versa. That is, every logic circuit has a corresponding Boolean expression. So far, we've assumed that some positive action takes place when a switch is closed, such as turning the light on. It is equally interesting and useful to consider the possibility that a positive action takes place when the switch is open. In this logic expression, for instance, the value of this function is inverse of the value of the input. So when the input is 0, the output is 1. When the input is 1, the output is 0. So when x equals to 0, the light is on, and when x equals to 1, the light is off. So instead of using the word inverse, it is more common to use the term complement. Thus we say that L of x is a complement of x in this example. Another frequently used term for the same operation is a NOT operation. So in short, NOT operation involves inverting or complementing the input. So these are the commonly used symbol of NOT operation, so a bar or a prime or an exclamation point or a tilde, or just writing it out like NOT x. So these are some examples of NOT operation used in more complicated logic expressions. The three logic operations that we've seen so far, namely NOT, AND, and OR, are implemented in digital circuits using transistors. And these circuit elements are called logic gates. A logic gate has one or more inputs that is a function of its inputs. It is often convenient to describe a logic circuit by drawing a circuit diagram or schematic consisting of graphical symbols representing the logic gates. A network of logic gates is often called a logic network or simply logic circuit. Here are the symbols of the logic gates that we've discussed so far. So this is the symbol of AND. This is basically a 2-input AND gate. And if you have n number of inputs, this is an n-input AND gate. And this is a 2-input OR gate. And you can have arbitrarily large number of inputs. So this is an n-input OR gate. And this is the symbol of NOT gate. Now we're going to talk about the precedence of the operator. So using the three basic operations, NOT, AND, and OR, it is possible to construct an infinite number of logic expressions. So parentheses can be used to indicate the order in which the operations should be performed. So it states that so we must know that in the absence of parentheses, operations in a logic expression must be performed in this order. NOT first, and then AND, and then OR. So in this here, for example, we have a logic expression with no parentheses. So the first thing that we need to do is that we need to do the NOT here. So x1 bar or x1 NOT and x2 NOT. We need to compute these two first. And then we perform the AND operation, that is x1 and x2 and x1 NOT and x2 NOT. And lastly, we perform the OR operation, because OR has the lowest precedence. So it is also common to omit the operator signs here, the AND signs, to simplify the expressions. Please also note that each of these variables here are binary, so they have only two possible values, 0 and 1. We have so far introduced the three most basic logic operations, NOT, AND, or OR, by relating them to simple circuits built with switches. Now this approach gives these operations a certain physical meaning. In other words, we can see that a logic expression can be converted to a circuit and vice versa. That is, a circuit or a logic circuit can be converted into a mathematical or Boolean expression. The same operations can also be defined in the form of a table called a truth table. So here on the left, we have the truth table of a 2-input AND gate. So on the left of the truth table, you have the input variables x1 and x2 here. Please also note that each of these variables here are binary, so they have only two possible values, 0 and 1. So what we do in the columns corresponding to x1 and x2 is that you list all possible combinations of the values of x1 and x2. 0, 0, 0, 1, 1, 0, and 1, 1. These are the four possible combinations. Again, if we observe the first two columns of x1 and x2 here, we see that the x1 and x2 values are not just listed randomly. The values are listed such that they form a row index of the truth table. What do I mean by that? So let me show you with the example truth table on the left, the two-input AND truth table. In the first row of this truth table, the value of x1 is 0 and the value of x2 is 0. The binary number 0, 0, 0, 0 is 0 when converted to decimal. So this is called the 0th row of the truth table. In the second row, the value of x1 is 0 and the value of x2 is 1. The binary number 0, 1 is 1 when converted to decimal, so this is the 1th row of the truth table. In the third row, the value of x1 is 1 and the value of x2 is 0. The binary number 1, 0 is 2 when converted to decimal, so this is the 2th row of the truth table. In the fourth row, the value of x1 and x2 are 1. The binary number 1, 1 is 3 when converted to decimal, so this is the third row of the truth table. So this is how truth table is organized, and all the combinations are taken so that the decimal number formed by these combinations also gives the index of the truth table. Now the rightmost column of the truth table indicates the function output for the corresponding row's input combinations. Thus when x1 equals to 0 and x2 equals to 0, AND gate output 0. When x1 is 0, x2 is 1, AND gets output 0. When x1 is 1 and x2 is 0, AND gets output 0. And when both of them are 1, only in this condition, AND gets output 1. So here on the right, we have the truth table of a 3-input AND gate. On the left of the truth table, we have the input variables x1, x2, and x3. Please also note that each of these variables are binary again, so they have only two possible values, 0 or 1. What do we do in the columns corresponding to x1, x2, and x3 is that you list all possible combinations of x1, x2, and x3, so 0, 0, 0, 0, 0, 1, up to 1, 1, 1, which corresponds to 0, 1, 2, 3, 4, 5, 6, and 7. So the values of the variables vary from 0, 0, 0 to 1, 1, 1, which represents decimals 0 to 7 respectively, and as usual, the rightmost column represents the output of the function. So this is the output of the AND 3-input AND gate. Okay, so now please pause this video and write down the truth table of a 2-input AND gate and a 2-input OR gate and a 3-input OR gate. So please pause this video and try to solve this problem, and then we'll match our answers. Okay, so hopefully you've been able to solve this. So you just list all the possible combinations and perform the OR operation and the OR operation. So OR is 0 when all the inputs are 0. For all other combinations, it's 1. The output is 1. Okay, so we need to understand two important terms about digital logic circuits. So the first one is analysis. So for an existing network, we can determine the function of the network. So this task is referred to as analysis. So analysis, basically, you already know the circuit, but you just don't know what the output of the circuit is. So The circuit is already built by someone else. You just don't know the output. So the process of determining the output is called analysis. The reverse task of designing a new network that implements a desired functional behavior is called synthesis process. This is the opposite process of analysis, where we don't have the logic circuit in advance or known, but we know what we're trying to design. It could be a burglar system, it could be a traffic light system. So what we do is that we perform a level of follow several procedures to actually build a circuit, and this building the circuit is called synthesis. The analysis process is rather straightforward and is much simpler in the synthesis process. So we'll treat analysis process in a detailed manner in this lecture, but we'll deal with the synthesis process in the next lecture. Okay, so what is the output of the circuit? So please pause this video and try to determine the output of the circuit, and then we'll match our answers. Okay, so hopefully I've been able to determine the output of the circuit. Here basically we're seeing an example of analysis. So we already had the circuit, we just needed to determine what it does. So here we're taking all the combinations of the values of x1 and x2. But if you notice, I haven't written the combinations randomly. If you compare the values of x1 and if you compare the value of x1 and the corresponding value of x2, we see that we have 0, 0, 0, 1, 1, 0, and 1, 1. Similar to the organization of the input variables of the truth table. We do this so that we can directly copy the output of the truth table here. What we did here is that we've written the output of each stage of each gate. So 0, 0, 1, 1 passing through a NOT gate. So when 0 passes through a NOT gate, it becomes 1. If the input to a NOT gate is 0, the output is 1. And if the input is 1, then the output is 0. And the input of a NOT gate is 1, then the output is 0. So in this manner, I had determined the outputs of each of the logic gates. And once we determine the final output of the final logic gate, beyond which we don't have any circuit. So this is our final output F. That's what we list in the truth table. An alternative way to express truth table is a timing diagram. Just like truth table, here we also represent the values of the variables but using figures like this. In this timing diagram, higher values are logic 1, lower value is logic 0. Timing diagrams actually represent clock pulses which have periods. So this timing diagram here has 4 periods. This one, 2, 3, and 4. So this timing diagram has 4 periods. In each period, the value of the variable doesn't change. So in each period, the value here is 0. In this period, in the second period, the value of x1 is 0. In the third period, it's 1. In the fourth period, it's 1. So if we compare the timing diagram with the logic circuit we have just analyzed, its function becomes clearer to us. You see, x1 is 0, 0, 1, 1, just like we have taken it here, 0, 0, 1, 1. x2 is 0, 1, 0, 1, 0, 1, 0, 1. And the output is 1, 1, 0, 1, and this is 1, 1, 0, 1. So a timing diagram is basically an alternative way to represent the truth table using a plot. Okay, now please pause this video and try to solve this problem. Please analyze this circuit, which means determine the truth table and also the timing diagram. So please pause this video and then we'll match our answers. Okay, so hopefully you've been able to solve this problem. So the output is 0, 1, 1, 0. Okay, so let's go back to the circuit that we were discussing earlier. So if we, let's say, mistakenly removed this AND gate in the bottom circuit here, these two circuits are exactly identical except the AND gate is removed. So if someone, let's say, accidentally removed this AND gate, we see that the circuit is still giving the exact same output. Since both of the networks realize the same function, it makes total sense to use the simpler one, the bottom one here, because it requires one gate less, which means it's less costly. So if someone would have told us to design a circuit that gives 1101, we could have either designed this one or this one, but this one is actually more cost efficient. So from this we've illustrated that we have found a very important property of synthesis. So synthesis output is not unique. So when the output is given, let's say someone told us to design a circuit that gives 1101. So this is basically synthesis by definition. So we could have either designed this circuit or this circuit. So the output of synthesis is not unique. You can design multiple circuits that give 1101, but the analysis output is unique. Please make sure that you understand this. So synthesis output is not unique. So if you're given the properties of a circuit and you're trying to design a circuit, you could end up with multiple solutions. One of these solutions could be better than the others. But for analysis, the output is unique because the function of a circuit will not vary with time. So that's the idea. So how then do we find the best implementation of a given logic function? So we'll try to answer this question in subsequent lectures. So how to design the minimum cost circuit, or how to perform minimum cost synthesis of a truth table. So we'll discuss it in the subsequent lectures. We'll also learn to synthesize any logic expression using NOT, AND, and OR gates. So we'll look into this in the subsequent lecture. But before that, I'd like to introduce another important logic gate called the XOR gate. This circuit we analyzed a few slides back. So this circuit was basically the XOR gate. Now notice this truth table of the XOR gate. Do you notice a pattern? So when both inputs are same, that is 0, 0 or 1, 1, the output is 0, and when both inputs are different, XOR gate outputs 1. So that's an easy way to remember the output or the function of XOR gate or exclusive OR gate, is that when both inputs are the same, the output 0, and when both inputs are different, the output 1. That's the symbol of XOR gate. And when you're writing it in an expression, use this symbol for XOR gate. And if you also compare this truth table with the truth table of a 2-input OR gate, there is stunning similarity. 0, 0 is 0, 0, 1 is 1, 1, 0 is 1, except for the last row. If it was the truth table of an OR gate, the output for the last row would have been 1. Now here it's 0. That's why it's called an exclusive OR gate, because it's like OR gate, but it's a bit of exclusive. So this logic function, or exclusive OR or XOR, which differs from the OR function only when both inputs are equal to 1, is useful for other applications. We're not going to talk about the formal way of doing synthesis, but here I'll show you an example so that you can have a general idea of what synthesis is. Let's say we're trying to design a circuit that can add two numbers. So let's say the two numbers are A and B here. Again, let's say these two variables are binary, so it's basically a 1-bit adder. So this variable can only take 0 or 1, and this variable can only take 0 or 1. Which means there are 4 possible combinations: 0, 0, 0, 1, 1, 0, and 1, 1. If we add 0 and 0, the sum is 0 and the carry is 0. If we add 0 and 1, the sum is 1, the carry is 0. If we add 1 and 0, the sum is 1 and the carry is 0. If we add 1 and 1, the sum is 0 and the carry is 1. So here we get the sum and carry, the two outputs of the truth table, and these are the inputs of the truth table. So with this information we can build the truth table here. So let's look into the truth table and observe. Do you see a pattern? We see that the S1 here is basically an AND gate. So it only outputs 1 when both of the inputs are 1. And S0 here is basically an XOR gate. So from this observation, we designed the circuit. So this is basically synthesis. We're given the characteristics or outputs of the circuit, and from this output, we're trying to design the circuit. So this is the final design. So this circuit basically is a 1-bit adder. It adds to 1-bit number. It's a very simple adder because it can only add 1 bit, but you get a general idea of what synthesis is from this example. And also, one last thing to note is that this truth table has multiple output variables, which is not a problem. This is also common. A truth table can have multiple input variables and multiple output variables as well. So we'll continue to talk about synthesis in the next lecture. So till then, if you have any comments, please feel free to write them in the comment section, and thank you.